a particular period of time and involve a particular number of packets. Okay. Here they are. Okay. And so then we have a number of such packet calls constitute a packet service session. Okay. And now these packets, of course, are transmitted not in synchronism, but there are random periods of time between successive packets. So the inter-packet call idle time is a statistical quantity. From here to here, there's a certain amount of idle time. From here to here, there's a certain amount of idle time, and so on and so forth. Right? And then after a packet session is over, okay, there is a timeout, an intersession idle time, until a new packet service session starts up. Okay. So we have here now a model where we have several new types of parameters. There is certainly the number of packets that constitute a packet call. How many of these packets are within a call? Then there may be several such packet calls within a packet service session. As you see here, there's one, another one over here, and another one over here that make up a packet service session. And then there is a timeout between such packet service sessions. And again, you have inter-packet times, and you have total packet service session times. So there are these new types of parameters now that ETSI uses to try to understand the probabilistic behavior of packet transmission systems. And of course, packet transmission systems are now everywhere, especially in the context of the internet, but also when you're transmitting stuff from your home computer or from your cell phone. Much of the traffic is organized in this particular manner. So we now need to get away from the Poisson model and ask the question, how do we model these kinds of statistical quantities like inter-packet times, number of packets in a packet call, number of packet calls in a packet service session, and inter-packet service session times. These are all statistically variable random processes. So here is what ETSI did. Okay. And again, it's based on monitoring various kinds of traffics and trying to fit well-known stochastic process parameters or models to the data. Okay. So here's what they came up with. The intersession idle time is modeled as an exponential random variable with mean value 1 over lambda sub is. Okay. So going back to over here, we say this particular time, this duration between the end of one packet service session and the beginning of another one, this variable here is modeled as an exponential variable in time with a particular mean value. And the particular mean value, of course, is determined by measurement, and it's called 1 over lambda sub is. Okay. So this is one number that we have to get a handle on. We have to measure that. The number of packet calls within a packet service session, again, has to be modeled, and that is modeled in this case as a geometric random variable, and the average value of that geometric random variable is mu sub pc. So going back to our model over here, we look at the number of packets, the number of packet calls within the packet service session, the number of packet calls within the packet service session. What did I do here? Here's what I'm, the number of packet calls within the packet service session. In other words, here is one, here's another one, here's another one. How many of those do you have in a packet service session? And this says that this is a geometrically distributed random variable. Now, what's a geometric random variable? Well, let's say I do a simple experiment. I flip a coin and I look at what's coming up, heads or tails, and I count the number of flips I have to make to the first head. Okay. So I flip the coin for the first time and it comes up heads, And the answer now is I took one flip to get the first head. But let's suppose instead the first flip is a tail, and the second flip is a head. Now the first head occurs on the second flip, or the first head could occur on the third flip, or the fourth flip, or the fifth flip. In other words, there is a random integer value here, and the geometric random variable is the distribution that counts how many flips it takes to the first head. And this is how this model is used over here. That is to say, the number of packet calls within a particular service session is a geometric random variable with its own mean value, mu pc. So if you know that number, then you have a probabilistic description of the number of packet calls within a packet service session. Then we have the inter-packet call idle time is also modeled as an exponential random variable. And again, we can go back here. What is the inter-packet arrival? The inter-packet time, that's the time between two successive packets inside of a packet call. So this particular time is also exponentially modeled. Okay. And then we have the number of packets within a packet call is modeled as a geometric random variable. So going back over here now, the number of packets in here, as opposed to the number of packets in a packet service session, is also modeled as a geometric random variable. So we have this geometric random variable, we have this geometric random variable, we have the amount of time between packets inside of a packet call, and we have the timeout between successive packet service sessions. Geometric random variables on the one hand, and exponential random variables on the other hand. Okay. So we have this particular statistical description now of how packet traffic arrives at a service point. Now there's one thing that's still missing, and that is the size of the packet. If you look at it here, the packet is larger than it is over here. And so we now need to figure out what is the number of bits inside one of those packets. And that is, again, a random variable. The ETSI traffic model, it is modeled as a so-called Pareto distribution. And we will look at that in a little bit, what a Pareto distribution looks like. Okay, so we have now two models for describing different types of traffic in a probabilistic manner. The Poisson point process describes how many arrivals or how many service demands you get in a particular period of time in a probabilistic way. The probability of you getting no traffic arrivals at all in an hour, or getting 5 in an hour, or getting 21 in an hour, is all described by this probability formula called the Poisson distribution, the Poisson random variable. And then the time between successive arrivals in this particular model is exponentially distributed. And all we need to know is the average value of the number of arrivals in a period of time of 1 second or 1 unit of time, and we've got the whole story. When it comes to packet type of arrivals or packet type of traffic, then the Poisson model doesn't work. And so ETSI, the European Telecommunications Standards Institute, came up with a different model based again on some very simple measurements. And the basic model then, as we saw, is the ETSI model, and it is based on measuring these quantities over here. For example, lambda sub is is the mean value of the intersession idle time, or mu sub pc is the mean value of the number of packet service session, the number of packet calls within a packet service session. So all you need to do is measure these average values, and you watch the traffic over a period of time, and you collect traffic and you average it out over that period of time. And the same thing for the other parameters. They're all based on simple distributions, geometric and exponential, And these are defined by the average values of these particular parameters. And then when it comes to packet size, we have a new kind of distribution called the Pareto distribution, and we'll get to that a little bit later. All right, so we have these two models, the Poisson model and the ETSI model. Very important. And it turns out that most of the cellular network development in terms of capacity deployment is really based on the ETSI model. Whereas most of voice traffic in the traditional telephone environment is really based on the Poisson model. So we have here now a situation where ETSI thinks that most traffic in these cellular networks or in these wireless networks is really packet type of network traffic. All right, we're coming to 8 o'clock now, so I'm going to quit. And I urge you now to write up in a couple of pages what you think you have learned today. So we talked about basically two things. One is the rationale for wireless networks. Why do we do it? What are the applications of wireless networks? And also, what are the advantages and the disadvantages of wireless networks? And then we talked about the types of wireless networks. And they're not just cell phone networks. There are a lot of other things too that connect together sensors, for example, or allow remote access to various kinds of devices. And we can talk about the types of networks that are local area networks as opposed to wide area networks. And we can even talk about body area networks where you have a heart monitor that transmits signals from your body to a watch on your wrist, from your heart to a watch on your wrist, these so-called body area networks. There are lots and lots of different types of wireless networks. It's not just all cell phones. Anyway, so we looked at that, and we also looked at now traffic issues. How do we characterize traffic? And we need to do this in order to be able to design an intelligent network capacity system that gives you the right throughput and the right quality of service and allows different applications to be conducted. So please write up your understanding of all of these things and then submit it. I hope that TA has in the meantime opened a folder for you where you can transmit that where you can upload that information, and then we will have a look at it, and if we find some misunderstanding, then we will correct that in the next lecture. Also, please remember that next Monday we don't have a lecture because of Martin Luther King Day. And so the homework assignment number 1, which focuses really on Poisson models of traffic, you can submit that homework assignment solution on or before February 1st. That is to say, before not the next lecture, but a week after the next lecture, when we will finish the discussion of traffic models, and then you can complete the assignment for that particular topic. Okay, I will then see you in 2 weeks from today.